Right. And welcome everybody to the next Delegate Assembly. My name is Greg Madejski. I will be presenting today, but I also will be hosting, so I have these two functions. We're going to, I'm with Rubin Community Science Team, and I work at Slack. I'll tell you a bit more about myself in a second. So the content of today's presentation is basically highlighting two Rubin Science Platform portal tutorials rather than notebook tutorials. And they'll be covering two different kinds of tables. And again, I'll get to this in a little bit. One of them will be the Minor Planet Center orbital parameters and solar system objects catalogs. And the second one will be solar system source and difference imaging analysis source tables. Again, I am astrophysicist by training, but primarily in the high energy astrophysics area. I was born and raised in Warsaw, went to college in Massachusetts, and now I'm a senior staff scientist at SLAC and also have a faculty position at physics department here, one of those visiting professorships. I'm very much a member of the Rubin Community Science Team. Bulk of my research was actually studying relativistic jets and active galaxies. And both using X-ray and gamma ray band and their origin of those jets, particle acceleration of those jets, and radiative processes. So my research interests are in high energy astrophysics and also in X-ray polarimetry in these days, because we have this new X-ray polarimeter that is flying in an orbit for the last year and a half or so. I'm interested in all aspects of active galaxies, and specifically in terms of Rubin, I would be really working on cosmology with strong lenses. But another area that I really feel very strongly committed to is the connecting broad range of multi-messenger astrophysics to Rubin. And that, of course, means X-rays, gamma rays, radio, very high energy neutrinos, gravitational wave events, and so on and so forth. So that's a little bit about me. As far as the agenda for today is, again, I'm the speaker today. At 9 o'clock, we'll start with announcements, and in about 5 minutes or so from now, we'll get going on the presentations. If you want to follow the presentations, I am providing you two tutorial links, and I can probably post those in the chat window. So let me just do that. Okay. Please be patient with me. And just in case if you didn't get the announcement. Okay, so let me copy this and put it into the chat window. Okay. Good. So, and again, if you want to follow the second portal, all you have to do is to replace the -1 with -2. So that's all there is. For first, I hope that I'll be able to get through both of those portal tutorials. They're not super short, so I timed myself, and I think I can barely make it in 1 hour. So let's see. I certainly want to have some time for questions and answers. And about 10 o'clock or so, or sooner or later, plus minus a few minutes, we'll go into breakout rooms. The main one will be for general questions and answers. And then if you want to have any specific breakout, you're very welcome to suggest it. We can actually add it to the breakout rooms. So I will not get started on breakout rooms yet, but I will continue with the presentation just a minute. But before we go any further, I wanted to tell you that we're going to have the next Delegate Assembly in 2 weeks, and that will be covering Notebook Tutorial 02, which is the tutorial about main belt asteroids. And Jeff Carlin, who's actually on call today, will be doing the presentation. And then we're going to have a bit more information about the details of the simulation overview, what's in the populations, and so on and so forth. And that will be by Pedro and Jake Kurlander. I believe Jake is actually on the call today. I think I saw him. And then on the 20th of October, we're going to have a special presentation by Meg Schwam, which will be basically the preparation for the Solar System Science Collaboration mini sprint. And I don't know the details of that yet. If any of you would like to maybe come up with any tutorials, any notebooks, maybe any sort of short scientific presentations, please get in touch with Melissa. We really like to have our assembly members to present as well, not only for us to be pontificating to you, but also to hear a bit more. So let me stop sharing at this point, this particular display, and maybe I could stop and open the floor for questions. I'm hoping that all of you already have Rubin Science Platform accounts, and you can join in and go into the portal account. If not, do let us know. We can probably make sure that you're all set. So is there anybody on the call who does not have an account?
Hi, Greg, it's Sherry here. I had an account before, but I haven't been able to log in, and I was hoping to get help, but we can do that afterwards.
Okay, one thing that you probably will need to do is you need to, hi Sherry, you need to get connected to Rubin Science Platform, and then when you try to get in, you will need an authentication, and I think your authentication will be through your university.
Yeah, I used to log in with GitHub, but I think that has changed, and I don't find my institute at the moment from the list. But maybe I don't want to hold up the call, so I think maybe I'll sort this out in the breakout afterwards.
Okay, so Jeff, should I make a breakout room for you and Sherry for a while? You want to do it later after my presentation? What do you think?
I can try and help out really quick, and I think I have the power to make a breakout if I need.
Okay, good. So why don't you go ahead and try to work with Sherry, and in the meantime, I'll just go through the introduction here. First, maybe first 5 or 10 minutes will be basically sort of very top level type introduction to DP0.3 and so on and so forth. Okay, so let me share my other screen, and I will be sharing here a different screen. It will be, hold on just 1 second, will be my Rubin Science Platform screen. Good, okay. So share this one and that should work. Okay, good. So now you can probably see my Rubin Science Platform. So when you enter the Rubin Science Platform, in the very beginning, you will actually start with the DP02 landing page. Today, we're going to be working only with DP0.3. And in order to get to that, those of you who are maybe not familiar with this, you need to go to this little box saying show on a upper right-hand side. And all of a sudden, you will see the new band showing up on top. And then you have to go to the second row from the top, and that would be LSST DP0.3 solar system objects. So now let me give you a little bit of a rundown of what DP0.3 is. Well, it's actually a simulation of solar system objects, and it only contains catalogs. There are no images in DP0.3. So those of you who worked with DP0.2 should know that we are running DP0.2 and DP0.3 are concurrent. They're running or you can access them in parallel. You might remember DP0.1 was actually replaced by DP0.2, but DP0.3 is something that is actually running in parallel. This is solar system, and in that particular simulation, only moving objects were simulated, and only catalogs were created. Again, there are no images, and DP0.3 is completely independent of DP0.2, and it's a hybrid catalog that contains both real and simulated solar system objects, such as asteroids, near-Earth objects, trans-Neptunian objects, and even apparently a few spaceships, but I don't know anything about that. There are no major planets in it, and for more information, you can actually go to the DP0-3 data products introduction, which is something that you can actually access directly from the link that I sent to you for DP0.3 portal tutorial. Okay, so now we're going to go through 2 tutorials today, and one of them will be MPC orbital parameters table and solar system objects table. So what I want to stress here is the first 2 tables really deal with the orbital parameters. There are really not individual point-by-point observations of sources. The second tutorial will cover basically those time-dependent or whatever time-resolved observations. So there are, as I mentioned, there are 4 tables in DP0.3 catalogs. But maybe before that, I should say that there are 2 different catalogs. You might have noticed that already. There's DP0.3 catalogs that are 1-year and 10-year catalogs. We're going to be only working in this tutorial. We're going to be working only with a 10-year simulation. Okay, so one thing that I should say is that the contents that are described in those are going to be in real observations when Rubin is operating. The tables will be constantly changing and they will be updated every day with the results of previous night's observations. But for this particular case, for DP0.3, they're only static catalogs. There's no change from one day to another. So that's the way it works. Basically, you have the same catalog when you log in today and when you log in a week or so, whereas it's different during the regular Rubin observations. So, and again, this tutorial will focus on the first 2 tables, the one that is MPC orbit table and solar system object table, and we will explore those individually. We will show how to join the 2 tables in multiple tables in the next tutorial, which will be focusing on solar system source and this different symmetry analysis source tables. In this particular case, let me just get started with what this MPC orbit table is. As I mentioned, during the daytime, after a night of observing, the solar system processing will actually put together, it will add the data to existing tables. And in the meantime, those will be reported to Minor Planet Center, and there will be the Minor Planet Center will calculate the orbital parameters, and those results will be passed back to Rubin and stored and made available to users as this NPC orbit table. Again, so you will have a lot of information from the previous night's observation, and that will be including also the observations from the past. So in this particular case, again, so this is slightly different than real life observations with Rubin. We have the static catalog rather than one that's dynamically updated all the time. And the Minor Planet Center did not actually recompute the orbital elements. I have a chat question. Let me just ask that. All right, I think Sherry is already all done. So great, wonderful, great, Sherry. So now you can follow it. Anyway, so the solar system object table, you can think of objects as being individual sort of planets, trans-Neptunian objects and so on and so forth, and you will be following them from one location to another. So that's what the solar system object table is, okay? The solar system objects, anyway, so you can probably read all this stuff for yourself. There is one little comment about absolute magnitudes that for solar system objects, absolute magnitudes are defined to be for an object at distance of 1 AU from the sun and 1 AU from the observer, and at the phase angle, which is angle between sun, object, Earth, to be 0 degrees. So it is, in a sense, an absolute magnitude of an object, just like for standard astrophysical sources. By the way,
Greg, sorry to interrupt, Tina. There's a request that you stretch your window out a bit, so it's a bit bigger.
Okay, sure. You mean something like that?
Probably also maybe if you could increase the font size a little bit, maybe if you can do that, that's possible.
That
if you're on a Mac, I think you can do it. The Command plus will do it.
Command. So is that better?
Maybe a little bit more.
Okay. So
one more.
Yeah. One more. Okay. All right. Good. So now you can.
Oh, thank you. Thank you.
All right. Great. Okay. Thank you. Thank you very much. All right. So one thing that we're going to do as a very first step, we're going to plot histograms of the orbital elements in this very first NPC orbit table. So again, the first step is logging in, getting into, you already have done it, getting into the DP0.3 solar system objects table. And again, you want to go into the, using this little arrow on the right-hand side, you can go into the NPC orbit table because that's the first one we're going to cover. Again, I have few things marked here, but that's sort of not important. You can actually start retrieving the first set of objects. So what we're going to retrieve here is basically by making a little check mark on the left-hand side, we're going to retrieve eccentricity and inclination of the orbits. And we're also going to we're going to retrieve the MPC absolute magnitudes, the H magnitudes, but we're going to also restrict them by putting the constraints column to be less than 20 magnitudes. Okay, so this is going to be my my query, and I'm going to basically this. By the way, I'm working now with a so-called user interface assisted way of accessing data. In a little bit, we're going to go for the second way of accessing the data, which will be using the astrophysical data query language, this ADQL language here. Okay, you can see this, hopefully seeing my cursor. You see edit ADQL. Okay.
And that is MPCH, right? Absolute magnitude H.
That's right, absolute magnitude H. So MPCH, there's a little check mark here, and I'm going to click now search. For the time being,
There's one question, sorry, in chat. You switch if you hit hide and then yeah, there you go. And then up at the top, somebody asked how to switch to DP3 rather than DP2. They missed it.
Okay. So all you need to do is to hit show.
Thank you.
And it appears. And here you can have a little arrow that now tells you can go back to DP0.2, you can go to DP0.3, and you can actually access other catalogs as well here. So, but for the time being, we just really want to work with this MPC orb catalog. And I already put the constraints, you can actually see them. And let me just hit search. For the time being, I'm restricting the row limit to be 50,000 because I don't want for the search to run for a long period of time. So this is just a selection of objects. This will not be a truly random sample, by the way. There will be any 50,000 objects in the table that match the query coordinates. The tables are typically sorted on some axis, so this can return preferentially objects in some region of the space. So go ahead.
Tudo bom? É rápido, né? Tava urgente?
I'm sorry, I don't understand.
Oh, Julio, I think you might be not muted.
All right, I think the person muted themselves. All right, so I'm going to search this, but there's, again, as I mentioned, this is not going to be a truly random sample. It might be from some kind of specific region of the sky because of the fact that tables are sorted on some axis. So in step 2, we will actually demonstrate the way to obtain a random sample of such objects. So let me get started on this. Okay, and this will take a little bit. And what you will see is basically on the right-hand side, this query returned the eccentricity, the inclination, and the magnitude for those objects. Again, this is a floating number. And the default plot will be the first 2 columns. So you can see that it's eccentricity versus inclination versus eccentricity. So now you can histogram those values, and the way you would do this, those of you who have not seen this, there is a little 2-geared icon, and you can click on that icon if you want to put something different than the first left 2 columns, and that will put a new query for the new little sub window that will allow you to put the new plot parameters. Since you want to do now a histogram, you probably will want to click onto something that says add new chart. And then in the plot type can be either histogram, you can also turn it into heat map, but for the time being, let's leave it at histogram. And the expression is, we want to see what is the distribution of eccentricities here. And once I hit E, notice that an E appears on the bottom, so you can hit on that and you're fine. And that will give you sort of by default number of bins would be 50, and that automatically will take the range from the existing table and will give you the bin width that is the range divided by 50. You can of course change this to 100 if you want to make a little finer distribution and so on and so forth. So let me click OK here. And now you can see, voila, you can see the distribution of eccentricities of all those objects. Very nice. So now for the time being, we don't necessarily need to have the eccentricity as a function of inclination. So let me close this table. And what I also will want to do is I will want to add one more plot, add new chart that will be distribution of inclinations. Okay, so I can type in inclination. And again, number of bends, I'm going to turn this into 100. And now second plot appears, okay? And now you can also do the same thing by adding one more plot, for instance, for the NPC H magnitudes again, and there will be adding new chart. Sorry, so that's what I meant to do. Great. So now you have 3 plots, and now you can, of course, play with those plots a little bit. You can, of course, go into trace options and chart options, but first of all, let's go into chart options. And for instance, maybe in this last one, you would like to have the vertical axis to be logarithmic. So you can actually go to log for the y, and you can apply. And when you close this, you can see now you have it in log space, okay? It's still listed as 10, 100, and so on and so forth, but it's placed in log space. All right, so maybe at this point, I should stop for a little bit, just in a case if I know if you have any questions. I think there might be some questions in the chat, so let me see. Somebody said, okay, Julio, thank you very much for closing the microphone. Great. All right, so now what I'm going to do is now I'm going to create a color diagram for the for some of the objects in this solar system object table. Now we're going to switch to the other table. Remember that so far we worked with this the NPC orb table. So now we're going to go into the second one. But maybe at this point, let me stop and ask whether people have any questions.
I have a question. Can you do the XY axis and then have histograms on the top and the sides? I know we can do that.
You know, I actually don't know how to do this, but I'm sure there is a way. Bob, I will try to find it. You would like to have, for instance, 4 different panels on the left-hand side, right?
Well, yeah, you know, I've done this before in the notebooks, but you've got your XY axis, and on the top it shows the Y histogram, the X histogram. On the side it shows the Y histogram at the same time. But it's not a big thing. I was just wondering. You don't have to do it.
Okay, I'll take a look on it and try to find it. I haven't actually played enough with the portal to see such detailed things, but sure. All right, so now let's go into the step 2, which will be creating of this color diagram of the solar system object table. So let me just close all the aspects here, and I can do this by clicking on RSP tab search. And what I'm going to do now is I'm going to show you how to use the astrophysical data query language. Okay, and again, from the UI assisted on an upper right hand side, I'm clicking on Edit ADQL. And at this point, again, you have to be sure that you're staying within the DP0.3 tab service, because otherwise the query that I'll load up in a second will not work. So let me just pick up this query to be able to at least select, in order to set up the random sample of DP0.3 solar system objects, you have to do a little bit of a trick. And I'm going to not maybe explain it in great detail, but I'm going to find out what is the total number of objects by entering a little query here. Again, this is my cheat sheet here. I'm going to go to tutorial number 1. Again, I'm going to cut and paste. So this is just, I'm revealing my shortcuts here. You can see that I'm now running from this window. I'm copying it from here into my other window. Of course, that's pretty straightforward. And now I can, again, execute this particular query. And again, I'm only selecting 50,000 sources here, maybe I can even select more to be able to.
I put it in the chat too.
Okay, you mean the my query? Perfect.
Yes, I don't know if they'll be able to copy it well, but I put it in there.
Okay, I just did. Okay, thank you. Great idea. So you can do this, and let's go ahead and execute it. And what all this will tell us is what is the total number of the entries in this particular table, and it's about 4 million. And also those solar system object IDs are sort of random numbers. So we're going to now select, this is a bit of a trick, you can actually figure out why we're doing this, but the whole idea here is to select some random number that will be approximately on the, we want to have on the order of maybe 120,000 objects or so. This is just sort of arbitrary number to make the demonstration relatively straightforward. And what I'm going to do is, again, the maximum number of objects is this 9,2 blah 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 and so on and so forth. So what I'm going to do is I'm going to enter another. I already did sort of those calculations in the past, so you can actually follow this in a tutorial. I'm going to enter another query that I'm going to again paste again into the chat window, which basically all I'm doing here is, you can follow this maybe offline, but all I'm doing here is I just want to make sure that I have 120,000 objects that are truly random. Okay, so I'm only selecting objects that have this solar system object ID greater than 866, which basically I did sort of back of the envelope calculations on a site. So let me just, I copied this, let me paste it in the chat window. Tina was
I beat you.
great, thank you, Tina. This is great. So now I'm going to again go back into my tab search. By the way, I can probably kill this guy. I don't need it. I don't need this either. So all I'm going to do is to go to tab search and again edit ATQL. Again, I'm going to clear this, paste it. Sorry, this is my previous one. I didn't quite copy it yet. So my apologies. I'm going to put into the DP0.3. Great. Okay, so again, what I'm selecting is this 120,000 objects that from this catalog called Asset Solar System Object Catalog, and I'm extracting the G color, G band magnitude, R band magnitude, I band magnitude, and Z band magnitude. And I'm going to eventually plot some of the colors against each other. So let me just go ahead and execute the search. Again, this is, as you see, it already takes a few seconds. So, you know, that's one of the reasons why I decided to restrict the numbers. And as a very first plot, the default will be, again, plotting the first two columns in a table on the right-hand side, but that's not what I really want to do. I would like to have a somewhat different of a trace here. Okay, so let me go to this window, and I'm going to modify this trace to have colors instead of just bands. So here there will be G minus R, and again, you can see that my window on the bottom, my little window appears with a new suggested entry. So this would be I magnitude minus Z magnitude, okay? And I'm going to maybe do a little bit more than 100 bins because, you know, I like to have slightly more elegant.
Okay, so that was G underscore H minus R underscore H?
That's correct.
Awesome.
Okay.
And then
I underscore H minus Z underscore H.
thank you.
Okay, good. All right, now I'm going to do one more thing. I know already from my previous experience that this grayscale is sort of not very attractive looking. I personally like to have yellow, orange, red. This is sort of a pretty bright. And I'm going to also restrict the colors. You can probably see that there is a bunch of objects that are sitting pretty far away from this G equal to R band. So, you know, actually, let me just apply this and you will see what I mean. Okay, notice that there is a huge spread in X and Y. I don't particularly like that. I want to just explore the objects that are most common here, and I'm going to go to chart options. And again, I'm going to, not for the time being, I won't bother putting the labels in, but for X min, I'm going to do 0. For X max, I'm going to do 1.5. I can see that you can see here that that most of the objects are really sitting close to the very center. And for while, I will go from -2 to 1, and I will apply this. Okay. Wow. Now you can see that there's 2 different populations of those objects. Clearly, some of them are, you know, have different colors than others. This is basically a random subset of the solar system objects. Notice that in this particular simulation, there are two sets of object colors. It probably will not be the case in real solar system objects. Again, Ruben will probably discover all kinds of very interesting bits with this particular solar system data set. So at this point, I probably should stop and maybe allow for at least a little bit of time for you to ask questions. By the way, I can slide my cursor back and forth and expand here a little bit and so on and so forth. So this is all very cool. So you can raise your hand, you can put whatever information you have in the chat window, however you want to do this. So at this point, while you're thinking about questions to ask, I want to sort of highlight a little bit what is here's a question. Meg, thank you. I'm very glad you're saying this. You're the expert. I'm far from being an expert. So she says that there are no asteroid families in DP0.3. There are only S and C types. Okay, that's what Meg is saying. So one thing I should mention here is a question came up from some of the people who are getting started on the on this data previews. When should we use Portal and when should we use notebooks? And the answer to that is, in my opinion, relatively simple. Notebook approach is much more powerful because it allows you to do all kinds of statistical studies and so on and so forth. On the other hand, you have to be already more familiar with how to use Jupyter notebooks and already know a bit how to, for instance, execute ADQL queries, how to run Butler, and so on and so forth. So in a sense, you can think of like it's the user interface driven or ADQL driven Portal queries are sort of for people who are getting started. And if once you get familiar with those, if you want to get more statistical, apply to more statistical tools, then you probably want to go to Jupyter notebooks. I don't know if any of you, Jeff, do you have any suggestions to, or anything else that you want to add to this sort of distinction between the two?
I'm not sure anything in particular. I mean, I think, yeah, as you were saying, just the portal is really nice for exploring. And then if you want to do deeper analysis of the things that you find in your explorations, then the notebook aspect can be more useful for that.
Good, thank you. All right, so now I'm going to switch gears, and I think I have probably enough time to go to the DP0, to the second one of those. The solar system source and difference image analysis source tables are in the second tutorial, and again, you can switch by basically replacing the -1 with -2 just before the RST or the. I have another question. Good. Okay, very good. Thank you, Bob. That's a good comment that you like to use Portal to see what all the variables are. Excellent. All right, Tina.
I posted the link.
Thank you, Tina. So let me do that. Okay, so let me go back to the portal. I'm going to go back into RSP tab search. Again, I am already in the LSST DP0.3 tab service, and it's sort of, we're going to be using almost exclusively at this point the ADQL search. So it sort of doesn't matter what's the what particular table you have on a right-hand side. So because your ADQL will actually select the proper table. All right, so let me just explain for a little bit what the solar system source table is. Again, as I mentioned, the solar system processing will report discoveries and data for moving objects to the Minor Planet Center, and that will be then used to compute the instantaneous 3D sky location. And the results will be again stored in the solar system source table, which has the one-to-one relationship with the difference image analysis source table. And again, the processing happens to be at night, and what will be formed is so-called difference images, and from those, the signal-to-noise ratio greater than type sources will be extracted. And after detection, the prompt pipelines will associate them into static sky transients and variables, and those DIA objects are not included in DP0.3. And again, the solar system processing occurs during the day, and at night of observing links together. It links together the DIA sources for moving objects into solar system objects. Okay, so but you can probably read some of the details in the sort of introduction part of the DP0.2 portal tutorial 2. But what we're going to do is right away, since I only have maybe about 20 more minutes, we're going to identify some objects to explore. And again, I'm going to explore first the solar system objects that will have very specific quantities. Will pick up a random subset of solar system objects that were observed between 100 and 300 times. This is again something I played around with, and those are the numbers that we selected. That will have Julio, you probably have a question, so go ahead.
Okay, so when an object is discovered by the LSST, it will not be included in this list until MPC has an orbit for it. Is this correct?
I am not 100% sure how that will work, but I think that's right.
Okay. Okay.
Okay, it's probably a lot of that information exactly about how it's going to be happening in solar system is probably written in the solar system data products definition document, DPDD. So you can probably find, I think that's ultimately the truth for that.
For currently for discoveries, it's not considered discovered until it has an orbit.
Okay, thank you very much, Melissa. That's very
Okay.
helpful. Okay, so let me just pick up the first from my crib sheet here from the second tutorial. I'm going to do the ADQL query, and again, one thing I will do in addition to that, I will just add it into the chat window, unless Tina already did. No,
I didn't yet.
Okay, I beat you to it, right? Excellent. Okay, so what this particular query is doing here, let me just go into edit ADQL, clear this one and add another one. Okay, what this query is doing, you can see it's selecting the number of observations, it's selecting the G magnitude, it's selecting the object ID, eccentricity, inclination, and Q, which is, I believe, semi-major axis here. Is that right, or is that and it's going to be extracting that from DP0.3 catalogs, this 10-year catalog, and specifically from the table called, here's an answer in chat. Sorry, thank you, Mike. This is, or Melissa, thank you. This is this perihelion, that's right. For many of those objects, of course, have a relatively not terribly eccentric objects, so, you know, the two are really not all that hugely different. So anyway, so, and we're selecting here only objects which have the G magnitudes between 17 and 20, and specifically want to make sure that the perihelion is less than 3. So this is basically relatively local objects. We're not going to have, for instance, trans-Neptunian objects, which is you will probably see it in one of the future assemblies. So let's just go ahead and select those objects. Basically, what we want to do here is, among others, to plot, for instance, the orbits of those sources. Okay, so let me hit search here. And that will return a table on the right-hand side, which I'm going to just slide back and forth a little bit with all the values that I requested. Again, the plot on the left-hand side is not terribly useful because just number of observations for an object with a different given magnitude. What we really want to do is we want to visualize one object's orbit, okay? And I'm going to select just one specific object which has object ID. This number is starting with 84. I mean, those 18-digit numbers are really hard to keep detailed tracks. This is just for you to visualize an orbit for an object, for instance. So we're going to do here is, so the previous search basically selected a bunch of data which you can then play around with. But now for this particular step, we're going to just visualize this one object's orbit. Okay, so let me copy this to the chat window again. And close my window here and go ahead and execute this. So this is copied now. Again, I'm going to go back to my tab search, edit ADQL, clear the current one, and paste a new one. And again, here it's going to be just visualization of the object's orbit. So here I'm hitting search. And this is actually quite cool because you can actually see right away what is the track of this object in heliocentric coordinates. You can see that it basically is moving on elliptical orbit, and you see that that's the for this particular object, this is basically at different times the position in heliocentric coordinates. What you can do is you can also visualize it in, for instance, in topocentric coordinates. So that's pretty straightforward. You can actually go to little gears, and instead of doing heliocentric, I'm going to just first do it in topocentric, for instance, X versus Y. Let me just do that.
Are you going to modify trace or add new trace?
I can do, yeah, I can add new trace, sure.
Okay, sorry.
Oh, no, that's fine. That's fine. This is sort of nice. So that's going to be a scatter diagram again. And again, this is going to be topocentric X. And in Y, we're going to do topocentric Y. Okay. All right. You can see that this object is moving all over the position on the sky in terms of the astronomical units. And it's, of course, has to do with the fact that it's relatively close to the sun. It's few astronomical units, but at the same time, Earth is going around the sun. So you can see that this is an effect of essentially the motion of both objects around the sun. So let me stop here for a second if anybody has any questions. By the way, Melissa, I really appreciate the fact that you're commenting here, because I'm not a solar system expert. As I mentioned earlier, extragalactic astronomy is really my bailiwick. So so thank you very much. Very appreciated. All right, now you can also visualize the object's two-dimensional sky motion, and that right now we basically are plotting the topocentric and heliocentric distances. But you can also do it. You can show the visualization of the objects in 2D by basically plotting RA and DEC as a function of maybe midpoint tie, which is basically a time of observation. So let me just again click on RSP tab search. So RSP tab search is now revealing the same table as before. Again, I'm going to do the same edit ADQL, and now I'm going to go to my cheat sheet and pick up the this search here. Again, this is going to be, I believe, the same object with the 125. And so let me copy this. Let me paste it into chat, and at the same time go into the display here and clear the ADQL query, and I'm going to add what I just copied. And notice that this is going to be the position in array, position, and deck as a function of time. So let me just search this for this particular object. And you can see the motion of the object in the sky. Now, of course, this is all very nice, but how is there any way to display? I don't know what happened here. So let me do by view tables. I think that's right. So
Yeah, I had to do that too, Greg. I had to hit the by view tables to change the view.
okay, great.
So other people might need to do that.
Right. Okay. Thank you very much, Tina, for mentioning this. Now, let me show you a really cool trick. Now, this is all wonderful, but you don't know which direction time goes here. So in order to display the time flow of this position of the object, what I'm going to do is I'm going to actually use a sort of cute trick here. I'm going to display a different color that will be actually representing the time. So I will use a color scale called rainbow, such that the colors going from, I don't remember if it's from red to blue or blue to red is the time progression. But I'm going to click on the settings icon again, and the pop-up window will appear. And I'm going to go to trace style, or trace options actually. And here we go. And I'm going to do, for color map, I'm going to use the time. Notice that this is the clever trick. I'm using MJD. Sorry. And the color scale I'm going to use as rainbow. So this is actually a trick that we discovered using our working with DP0.2, that you can actually create a third dimension by applying some kind of color. Okay, so I'm basically using my time as a color map. Okay, and now you can see, once you close this, you can see that there is this motion probably from, this is 614, and this would be 63, this would be 618, so, and this is 62. So you can actually translate the two, but you can actually see the visual, this is a visualization of the motion of this object across the sky in the Rubin detections. All right, so I want to do one more step. I want to go back and try to visualize the photometry of maybe the same object in basically just an R band. Okay, so now I'm going to use step 4 in our tutorial. Let me go back to my tutorial here.
Hi, Greg.
Yeah, I have a question here.
Yeah, before you move on, do you know if you can add a color bar to the plot that shows you what the color represents?
We tried, and no, not yet. That will eventually come in a subsequent version of the portal instance of the Rubin Science platform.
Great, thanks.
Yeah, sure. Again, if you want to do anything super fancy for publication quality and stuff like this, you probably will have to do it in some kind of a plotting package that will allow you to put the bar. All right, so now I'm going to do the next step, which is basically visualization of the object's photometry. So again, we're going to go to the same RSP tab search, and I'm going to copy this again into the chat window. And again, it's the same object, the one which ends with 25. And I'm going to paste this into my new tab search, edit DQL. So hopefully at this point you're becoming somewhat familiar with the sort of the nuts and bolts of the portal. I think that I find the portal to be really useful, and there's so many things that you can discover by just basically clicking on different icons. But let me just continue with my presentation here. So let me search on this one. And now, as default, you're getting the magnitude in the x-axis and the time of observation in y-axis. That's not so great. So let me do, again, a different display here. Let me just click on the 2 gears, and for X, I'm going to use this midpoint MJD, and for Y, for the first, maybe we can do a magnitude, okay? Right? And for trace will be just, all right, so here we have this midpoint MJD, and if you want to have it even more elegant, you can subtract 60,000 from this, and that will give you a bit minus 60,000. Let me apply this, and this will give you a little bit more of a sense of how many days there are instead of having this exponential notation here. Okay, I can add new trace. Okay, and for that new trace, now what I can do is I can do, for instance, the time evolution, for instance, of the, let's make it, for instance, of phase angle. Okay, so for this, I'm going to do again the midpoint tie minus 60,000. For Y, now I'm going to do phase angle. Okay. All right, so there isn't really any clear relationship between the change of phase angle with time. I'm not an expert here. I don't know very much about this particular object, but instead of just giving you a very clear scientific presentation, this is really sort of more aimed to have you see what are different ways of actually use the portal aspect of the Rubin Science Platform for the purpose of the of working with the data and the DP0.3. Again, the nuts and bolts of the Rubin Science Platform are basically very similar, if not exactly the same, for the DP0.2. It's just that the DP0.2 allows you to display images in addition to examine and search catalogs. So again, as I mentioned earlier, there are no images, and the DP0.3 is just catalogs, but there's plenty of really interesting and cool information you can extract from those. There will be more on this probably within another maybe about 2 months or so, when I have a next tutorial, more advanced tutorial that will be ready, that will start to explore more data in the DP0.3. I think I'm doing reasonably well with time, so I will have plenty of time for questions, and then we can set up breakout rooms. So please go ahead and ask questions, and if you want to, I can sort of revisit individual steps. All right, so if you want to play with this, there are a few additional exercises for the learner here. They are listed on the very bottom. You can use a different object to repeat the same exercises here. If you want to be a little bit more ambitious, you can actually start playing with instantaneous x, y, z velocities in addition to the distance. And then you can plot the velocity as a function of distance and so on and so forth, and see whether the objects indeed move slower when they're farther away from the sun, which is what you'd expect from Kepler's laws. And then there's, you can actually determine, start playing around a little bit with the astrometric scatter and so on and so forth. So plenty of different tools you can play with here. But just in the very beginning here is a lot more information about what is the content of the SS source table and the IA source table. So all right, thank you, Bob, for your applause. So at this point, I will stop sharing, and maybe I will actually, I think at that point, we can probably stop recording as well. I don't see much of a point of continuing to record, so let me stop recording and